So let's look at how we can find the length of a curve that's described in polar coordinates, so the length of a polar curve. Now, if you remember, when we found slope in polar coordinates, we used the fact that you can easily parameterize a polar curve, and then we just used what we knew about slopes of parametrics. So we're going to do the same thing here. We are going to parameterize the curve and then use what we know about length of a parametric. So, say we have this curve, r equals f of theta, and theta is running from alpha to beta. So we've got some piece of our curve. So remember, parameterized x is f of theta cosine theta, because in polar coordinates, remember, x is r cosine, but when you're on the curve, r is restricted to some function of theta. And likewise, y is r sine theta, but on the curve, it's restricted to that function. So there's our parameterization. And now we're just going to use our parametric arc length equation to handle those. So we know that for a parametric, it would be the square root of dx d theta squared plus dy d theta squared. And so when we take the derivative of x with respect to theta, that requires product rule. So f prime theta cosine minus f sine quantity squared plus, we take the derivative of y with respect to theta. That's also going to require a product rule. So f prime sine plus f cosine squared d theta. So now we have our arc length formula. And remember, we did a similar thing with slope. We just took the ratios of dx d theta and dy d theta. But this actually, there's a lot of similarities going on in here. And there's a lot of sine squareds and cosine squareds. So what we can do, it's going to be a mess for a second. But if we multiply this all out, a lot of stuff is going to cancel. This actually reduces down to a much nicer formula. Hopefully I can fit it all on the screen. So when I FOIL this, you're going to have the first term squared. So that's f prime squared cosine squared. Then when you FOIL out, you get the product of those two terms twice, right? So you're going to get minus 2 f prime sine cosine. And then lastly, that second term squared. And I'm definitely not going to be able to squeeze the rest in there. So I'm going to write it right underneath. And actually, that might make it easy when we start matching up what we're going to do here. So still under this square root is that squared, which is f prime theta squared sine squared. Now it's going to be plus 2 times all that multiplied together, which is exactly this, right? But now with a plus. These two things look different, but the combination of those two terms have a f prime sine cosine. So we have plus 2 f prime sine cosine. And then we're going to have this one squared. So we're adding that first line to the second line. And actually, this is nice because this comes out with like terms. The middle's gone, right? That and that are opposites. But look at this. These both have an f prime squared in them, right? I'll do this in 2 steps, but we're going to take advantage of an identity. I could factor out that f prime squared. And it's being multiplied by sine squared plus cosine squared. Here, these both have a f squared in them. And when you factor that out, you have sine squared plus cosine squared. But that is our classic Pythagorean identity. Sine squared plus cosine squared is 1. So that's 1. That's 1. So this whole thing is just the integral from alpha to beta of f prime squared plus f squared. So before, when we did slope, I said, oh, don't bother memorizing the formula. You can always just rederive it by taking these derivatives. This I would definitely memorize, because you do not want to have to rederive this every time you do an arc length. And this is so easy to remember. It's just the function squared plus its derivative squared. Typically, I guess it's written the other way around. I think you'll even see in the textbook, because f is r, and that's a derivative with respect to theta, you might see it as r squared plus dr d theta squared is another way you might see it written. But that's saying the exact same thing, just whether you write r or f of theta or prime notation or Leibniz notation. So same thing, different notation, whoops, from alpha to beta. So next time we'll look at an example of using this formula.